Hi, and welcome to Tech Guru Space with Google Compute Engine Architecture Virtual Network course. My name is Jessie Mediratha, and let's get started. In this module, we will be covering virtual networks. Google Cloud uses a software defined network that is built on a global fiber infrastructure. This infrastructure makes Google Cloud one of the world's largest and fastest networks. In this module, we'll start by introducing Virtual Private Cloud or VPC, which is the Google's managed networking functionality for your cloud platform resources. Then we will look at networking into its fundamental components, which are projects, networks, subnetworks, IP addresses, routes, and firewall rules, along with network pricing. After that, we'll look at some common network designs. So as in the previous video, this map represents Google Cloud. On a high level, Google Cloud consists of regions, which are the icons in blue, points of presence, which are the dots in blue, a global private network, which is represented by a blue line. A region is a specific geographical location where you can run your resources. So this map shows several regions that are currently operating as well as future regions. Regions indicated with blue icons have three zones. Lower is an exception. So where the region called US-Central 1 has four zones, US Central 1A, US Central 1B, US Central 1C, and US Central 1F. The POPs are where Google's network is connected to the rest of the internet. Google Cloud can bring its traffic closer to its peers because it operates an extensive global network of interconnection points. This will reduce the cost and provides user with a better experience. The network contains regions and POPs and is composed of a global network of fiber optic cables. Let's talk about Google Cloud Network and specifically let's focus on the Virtual Private Cloud or VPC. With Google Cloud, you can provision your Google Cloud resources, connect them to each other, isolate them from each other in a VPC. You can also define fine-grained networking policies within Google Cloud and between Google Cloud and on-premises or other public clouds. Essentially, VPC is a comprehensive set of Google managed networking objects. Let me give you a high level overview of these objects. Projects, the first one, are going to encompass every single service that you use, including networks. Networks come in three different flavors: default, auto mode, and custom mode. Subnetworks allows you to divide or segregate your environment. Regions and zones represents Google's data centers, and they provide continuous data protection and high availability. VPC provides IP addresses for internal and external use, along with granular IP address range selections. Let's start exploring the VPC object by looking at the project, networks, and subnetworks. So projects, what are projects? So projects are the key organizers of infrastructure resources in Google Cloud. A project associates objects and services with billing. Now, it's unique that projects actually contains entire networks. The default quota for each project is 5 networks, but you can simply request additional quota using the Cloud Console. These networks can be shared with other projects or they can be paired with networks in other projects. These networks do not have IP ranges but are simply a construct of all the individual IP addresses and services within that network. Google's cloud network are global, spanning all available regions across the world that I talked about in the earlier slide. So you can have one network that literally exists anywhere in the world, Asia, Europe, America, all simultaneously. And inside a network, you can segregate your resources with regional subnetworks. Every project is provided with a default VPC network with preset subnets and firewall rules. Specifically, a subnet is allowed for each region with non-overlapping CIDR blocks and firewall rules that allow ingress traffic for your ICMP, RDP, and SSH traffic from anywhere, as well as ingress traffic from within the default network for all protocols and points or ports. In an auto mode network, one subnet from each region is automatically created within it. The default network is actually an auto mode network. So these automatically created subnets use a set of predefined IP ranges with a /20 mask that can be expanded to a /16. All of these subnets fit within the 10.128.0.0/9 CIDR block. Therefore, a new cloud, Google Cloud regions become available. New subnets in these regions are automatically added to auto mode networks using an IP range from that block. A custom mode network does not automatically create subnets. So this type of network provides you with complete control over its subnets and IP ranges. You can decide which subnets to create in regions you choose and using the IP ranges you specify within the RFC 1981 address space. These IP ranges cannot overlap between subnets of the same network. Now you can convert an auto mode network to a custom mode network as well to take advantage of the control that custom mode network provide. However, this conversion is one way, meaning that custom mode network cannot be changed to an auto mode network. So be careful, review your considerations for auto mode networks to help you decide which type of network meets your needs. On this slide, we have an example of a project that contains 5 networks. All of these networks span multiple regions across the world, as you can see on the right. Each network contains separate virtual machines, A, B, C, and D. Because VMs A and B are in the same network, network 1, they can communicate using their internal IP address, even though they are in different regions. Essentially, your virtual machines, even if they exist in different locations across the world, take advantage of Google's global fiber network. Those virtual machines appear as they are sitting in the same rack, and when it comes to a network configuration protocol, VMs C and D, however, are not in the same network. Therefore, by default, these VMs must communicate using their external IP addresses, even though they are in the same region. The traffic between VMs C and D isn't actually touching the public internet, but is going through the Google Edge routers that has different billing and security ramifications that we will explore later. So because VM instances within a VPC network can communicate privately on a global scale, a single VPN can securely connect your on-premises network to your Google Cloud network, as shown in this diagram. So even though the two VM instances are in the separate regions, which is your US West one and US East one, they leverage Google's private network to communicate between each other and to an on-premises network through a VPN gateway. This reduces cost and network management complexities. I mentioned that subnetworks work on a regional scale. Because a region contains several zones, subnetworks can cross zones. So this slide has a region 1, with two zones, Zone A and Zone B. Subnetworks can extend across these zones within the same region, such as Subnet 1. The subnet is simply an IP address range, so you can use an IP address within that range. Notice that the first and the second address in the range 0 and 1 are reserved for the network and the subnet gateway, respectively. This makes the first and the second available address 2 and 3, which are assigned to the VM instances. The other reserved addresses in every subnet are the second to last addresses in the range and the last addresses which is reserved as the broadcast address. So to summarize, every subnet has four reserved IP addresses in its primary IP range. Now, even though the two virtual machines in this example are in different zones, they still communicate with each other using the same subnet IP addresses. This means that a single firewall rule can be applied to both VMs, even though they are in different zones. Speaking of IP address of a subnet, Google Cloud VPC lets you increase the IP address space of any subnets without any workload shutdown or downtime. So this diagram illustrates a network with subnets that have different subnet masks, allowing for more instances in some subnets than others. This gives you flexibility and growth options to meet your needs. But there are some things to remember. The first, the new subnet must not overlap with other subnets in the same VPC network in any region. Also, the new subnet must stay inside the RFC 1918 address space. The new network range must be larger than the original, which means the prefix length value must be a smaller number. In other words, you cannot undo an expansion. Now, auto mode subnets start with a /20 IP range, so they can be expanded to a /16 IP range, but no larger. Alternatively, you can convert the auto mode subnetwork to a custom mode subnetwork to increase the IP range further. Also, avoid creating large subnets. So, overly large subnets are more likely to cause CIDR range collisions when using multiple network interfaces and VPC network pairing, or when configuring a VPN or other connections to an on-premises network. Therefore, do not scale your subnet beyond what you actually need. Now that we've covered Google Cloud Network at a high level, let's go deeper by exploring the IP addresses. In Google Cloud, with virtual machine can have two IP addresses assigned. One of them is an internal IP address, which is going to be assigned via a DHCP internally. Every VM that starts up and any service that depends on virtual machines get an internal IP address. Examples of such services are App Engine and Google Kubernetes Engine, which uh, we are not going to explore in this course. When you create a VM in Google Cloud, its symbolic name is registered with an internal DNS service that translates the name to the internal IP address. So DNS is scoped to the network, so it can translate web URLs and VM names of hosts in the same network. But it can't translate host names from VMs in a different network. The other IP address is the external IP address, but this one is optional. You can assign an external IP address if your device or your machine is externally facing. The external IP address can be assigned from a pool, so making it ep- ephemeral, or it can be assigned a reserved external IP address, making it static. If you reserve a static external IP address and do not assign it to a resource, such as a VM instance or a forwarding rule, you are charged at a higher rate than for static and ephemeral external IP addresses that are in use. So, regardless of whether you use an ephemeral or static IP address, the external address is unknown to the OS of the VM. The external IP address is mapped to the VM's internal address transparently by VPC. Each instance has a host name, so that can be resolved to an internal IP address. This host name is the same as the instance name. There is also an internal fully qualified domain name or FQDN for an instance that uses the format shown on this slide. So if you delete and recreate an instance, the internal IP address can change. This change can disrupt connections from other compute engine resources, which must obtain the new IP address before they can connect again. However, the DNS name always points to a specific instance, no matter what the internal IP address is. Each instance has a metadata server that also acts as a DNS resolver for that instance. The metadata server handles all DNS queries for local network resources and routes all other queries to Google's public DNS servers for public name resolution. I previously mentioned that an instance is not aware of any external IP addresses assigned to it. Instead, the network stores a lookup table that matches the external IP address with the internal IP address of the relevant instances. Instances with external IP address can allow connections from hosts outside of the project, so users can do so directly using the external IP addresses. Public DNS records pointing to instances that are not published automatically. However, admins can publish these using existing DNS servers. Domain name servers can be hosted on Google Cloud using Cloud DNS. Cloud DNS is a scalable, reliable, and managed authoritative domain name system or DNS service running on the new infrastructure as Google. So Cloud DNS translates requests for domain names like google.com into IP addresses. Cloud DNS uses Google's global network of anycast name servers to serve your DNS zones from redundant locations across the world, providing lower latency and high availability for your users. High availability is very important because if you can't look up a domain name, the internet might as well be down. That's why Google Cloud offers a 100% uptime service level agreement SLA for domains configured in Cloud DNS. Cloud DNS lets you create and update millions of DNS records without the burden of managing your own DNS servers and software. Another networking feature of Cloud DNS is alias IP address. So, an alias IP address lets you assign a range of internal IP addresses as an alias to a virtual machine network interface. This is useful if you have multiple services running on a VM and you want to assign a different IP address to each service. In essence, you can configure multiple IP addresses representing containers or applications hosted in a VM without having to define a separate network interface. You can draw the alias IP range from the local subnet's primary or secondary CIDR range. So this diagram provides a basic illustration of primary and secondary CIDR ranges and VM alias IP ranges. By default, Every network has routes that let instances in a network send traffic directly to each other, even across subnets. In addition, every network has a default route that directs packets to destinations that are outside the network. Although these routes cover most of your normal routing needs, you can also create special routes that override these routes. Just creating a route does not ensure that your packets will be received by the specified next hop. So firewall rules must also allow the packets. The default network has pre-configured firewall rules that allow all instances in the network to talk with each other. Manually created networks do not have such rules, so you must create them manually. Let's go through some pricing. So this table is from compute engine documentation and it lists the price of each traffic types. First of all, ingress or traffic coming into the Google Cloud network is not charged unless there is a resource such as a load balancer that is processing ingress traffic. Responses to request count as egress and are charged. The rest of this table lists egress or traffic leaving a virtual machine. Egress traffic to the same zone is not charged as long as that egress is through the internal IP addresses of an instance. Also, egress traffic to Google's product like YouTube, Map, Drive, or traffic to a different Google Cloud service within the same region is not charged for. However, there is a charge for egress between zones in the same region, egress within a zone if the traffic is through the external IP address of an instance, and egress between regions. As for the differences in egress traffic to the same zone, compute engine cannot determine the zone of a virtual machine through the external IP address. Therefore, this traffic is treated like egress between zones in the same region. So now you are charged for static and ephemeral external IP addresses. This table represents the external IP pricing for US Central 1 as of this recording. And you can see that if you reserve a static external IP address and do not assign it to a resource such as a VM instance or a forwarding rule, you are charged at a higher rate than for static and ephemeral external IP address that are in use. So also external IP addresses on preemptible VMs have a lower charge than for standard VM instances. Let's cover the network architecture. So let's look at some architectures. Let's start by looking at the availability. So if your application needs increased availability, you can place two virtual machines into multiple zones, but within the same subnetwork, as shown on this slide. Using a single subnetwork allows you to create a firewall rule against the subnetwork 10.2.0.0/16. So therefore, by allocating VMs on a single subnet to separate zones, you get improved availability without additional security complexity. A regional managed instance group contains instances from multiple zones across the same region, so which provides increased availability. Now let's look at globalization. So in the previous design, we placed resources in different zones in a single region, which provides isolation from many types of infrastructure, hardware, and software failures. Putting resources in different regions, as shown on this slide, provides an even higher degree of failure independence. This allows you to design robust systems with resources spread across different failure domains. So when using a global load balancer like the HTTP load balancer, you can route traffic to the region that is closest to the user. This can result in better latency for your users and lower network traffic cost for your project. Now, as a general security best practice, I would recommend using only assigning internal IP addresses to your VM instances wherever possible. CloudNet is Google's managed network address translation service. It lets you provision your application instances without public IP addresses, while also allowing them to access the internet in a controlled and efficient manner. This means that your private instances can access the internet for updates, patching, configuration management, and more. Now, in this diagram, CloudNet enables two private instances to access an update server on the internet, which is referred to as outbound net. However, CloudNet does not implement inbound net. In other words, hosts outside your VPC network cannot directly access any of your private instance behind the CloudNet gateway. This helps you keep your VPC networks isolated and secure. Similarly, you would enable private Google access to allow VM instances that only have internal IP addresses to reach the external IP addresses of Google APIs and service. For example, if your private VM instances needs to access a cloud storage bucket, you need to enable private Google access. You enable private Google access on a subnet by subnet basis. As you can see in this diagram, subnet A has a private Google access enabled and subnet B has it disabled. This allows VM A1 to access Google APIs and services even though it has no external IP addresses. Private Google access has no effect on instances that have external IP addresses. That's why VMs A2 and B2 can access Google API and services. The only VMs that can't access those API and services is VM B1. The VM has no public IP address and it is in a subnet where Google private access is also disabled. So, question time. Our first question. In Google Cloud, what is the minimum number of IP addresses that a VM instances needs? First, which is one, only an internal IP address. B, two, one internal and one external IP address. Or C, which is three, one internal, one external, and one alias IP address. And our correct answer is A. So in Google Cloud, each virtual machine needs to have an internal IP address. The external IP address is optional, therefore a VM instance only needs one IP address. Next question. What are the three types of networks offered in the Google Cloud? A, which is zonal, regional, and global. B, which is a gigabit network. 10 gigabyte network, and 100 gigabyte network, or C, which is default network, auto mode network, and custom mode network, or the last one, which is IPv4 unicast network, IPv4 multicast network, or IPv6 network. The right answer is C, which is the three network types offered by Google Cloud are default, auto, and custom. Each project starts with a default network. The auto type network uses the same subnet IP ranges as the default type with a network name other than the default. So a custom type allows you to specify the IP ranges of the subnets. Let's move on to the next question. What is one benefit of applying firewall rules by tag rather than by addresses? So A, tags help organizations track firewall billing. B, tags in network traffic help with network sniffing. C, tags on firewall rules control which ephemeral IP addresses VMs will receive. Or D, when a VM is created with the matching tag, the firewall rules apply irrespective of the IP addresses it is assigned. And the correct answer is D. So when a VM is created, the ephemeral external IP address is assigned from a pool. There is no way to predict which address will be assigned. So there is no way to write a rule that will match the VM's IP address before it is assigned. Tags allow a symbolic assignment that does not depend on order in the IP address. So it makes more simpler, more general, and easier to maintain firewall rules. Thank you, and I look forward to seeing you in the next module.